stage 3. Okay, so opponent, please challenge.
We call the topic 3 latter.
Please, number 3. Accept. Okay, accept.
有机会，看他们跑得多快。
reporter, please take the floor.
Okay, I'm the reporter from Iowa, and I'm Zoe Chi. Today I'm going to present question number 3, Lotto Lotto. And this is a problem statement. Attach a ball to each end of the string, connect center of the string to a probe. When the probe oscillates along the vertical direction, the balls start to collide and oscillate with increasing amplitude. Investigate this phenomenon. And our main focus is on the amplitude, the increasing amplitude, and the frequency. This is our outline. And this is the observation video. Through this video, you can see that when when the ball is oscillated, then they will just be more high here. And this is the theory, equation of motion. And that one is the modified equation. Introduce resistive force term. And then the tau equals to 1 divided by beta is time for the amplitude to decay to the 1 divided by e of the initial value. And when the decay rate and when the tau is smaller, then it means that faster energy dissipation. And this one is the amplitude erosion, and that one is this one is the relationship of the COR and the beta. And by seeing that one, you can see that energy decays twice as fast as amplitude. And that one is the quality factor. Measure the oscillation efficiency. And this is the 3 type of damping, and we will talk about in the later. This is the theory of resonance. Since for example, pendulum, the period is the time it takes for a pendulum to complete one full oscillation. But however, in the Lotto system, resonance occurs when frequency of the applied force match the system's half efficiency, leading to an amplified oscillation. That's because that in the Lotto, it's not just going to here. It's only they meet each other in the middle. So that's what is the half period. And however, the energy transfer process is complex and depends on factors like the elasticity of the coulomb and the system damping. And I want to talk about the damping ratio and the quantity factor determines the shapeness and effectiveness of resonance, affecting how long the system sustains oscillation before energy loss dominance. And this is the theory of the conservation of momentum. I'm talking about this because from the drawing, you can see that they will exchange when there's no force to put the Lotto up, then they will change the height due to the conservation of the moment. And if you have a force to put the Lotto higher, then and there's a force given that by that, they will increase the same height. And this is my experimental design. I used the earthquake equivalent to control the force and the frequency of the in my experiment. And the reason why I mark the different colors of the balls is because that it's easier for me to track on it. And this is the result without the force. I'm just tracking the damping of the lotto but without the force. And through this, you can see that the energy decays follows an exponential function given by that. And since energy is proportional to the square of the amplitude, we can express this as this. And from our fit, we determine the damping coefficient as the damped oscillation parameters. The damped natural frequency is given by this one. And finally, the damping ratio is this. And by deep into the damping ratio, you can know that this system is underdamped. And it means that the oscillation with decaying amplitude. And by knowing the theta, so that you can reverse the coefficient of resistance, which is 0.4. And it means that this system is an elastic collision. And by this equation, you can know that the period is 0.81. And for the explanation of the resonance, you can if I give the same force but different frequency, you can see that the differences with the resonance. If there's resonance happen, then the balls will go to the higher. And this is the result. By knowing the frequencies of the system, you can, through the equation, to know when will the resonance happen. And you can see that there's the peak of the amplitude, and it happens almost at 2.48. And this is the comparison of the peak of the frequency during resonance. And the blue point is I used Python to simulate the system, and the orange point is the real result in the reality. So you can see that they are almost matched. And this is my result for see it more clearly. This is the amplitude time diagram. And you can see that no matter does it happen resonance, eventually, if you give the same frequency for the whole time, then you can see that eventually it will get to a constant, and the amplitude won't change. So for my conclusion is that by controlling the frequencies of the lotto, you can know that eventually there will be a constant and they won't change. And also, you can see by the further experiment that this system is not an elastic system. Also, the frequencies of the force equals to the resonance happens when the frequencies of the force is equals to the 2 times of the frequencies of the system. So this is all of my report. Thank you.
Okay, so comment.
peninsula? How exactly did you oscillate this system?
There's a line. Did you see it? To connect with the earthquake equipment, so you can control the force and the frequency, right?
Okay. Did you measure the mass of both of the balls?
No, because I don't think.
How do you know how much energy is needed to? How do you calculate the energy of the system? Do you know the mass?
Sorry, I did. The energy I calculate is the.
Do you know the mass of the balls?
Sure.
Yes, I know. This is the energy.
What are the two masses?
One I know the actual sorry for my memory. After that, it's almost at 12.9.
Okay, that's fine. Did you try to change the ball's material in your trials?
Yes, I used the golf balls and used the ping pong balls, but eventually I see that the golf balls have a better result and a more obvious result.
Okay. You know how lateral there's like an angle theta here. What is the largest angle that you measured in your experiment?
The largest angle that I measured is
60. Okay.
Hands up. Yeah, the comment, please.
I'm I'm Steven, and I will be opposing Lado question number 3 for the all-nighters. So here's the problem statement, and from our point of view, we think that the ideal structure of the investigation should be to develop a model and derive the relevant equations and come up with the relevant parameters. I think the reporter did not come up with enough parameters to really prove this phenomenon. Next, to explain forces derivations, experimentation and explanation, and then finally error analysis, which I also think they missed. Here was the opponent structure. They started with their theory and model, which is based on dampening and also conservation of momentum. Their experiment was tracking energy over time, however, it was pretty unclear how they did so. And finally, analysis, they talked about resonance as well as how amplitude diminishes. Some pros were that they had good demonstration videos and a lot of visuals to help understand the concepts, but their voice could be clear. They had a lack of parameters. I did not hear any mention of centripetal force, tension, gravity, any of that. Bad time management, and there's not enough data sets shown to really prove their theory. And here are the discussion questions I want to talk about. First one, the largest angle, they measured is 60 degrees, and this is a very big limitation, and I'll explain why later. And there's unclear energy and error because they don't even know what the mass of their balls is. How are they going to conduct conservation of momentum? They did not have any error analysis. I think that is an oversight on their part. And then I think that they should have also talked about chaos in the system because the initial conditions of lateral does not necessarily determine the path. So that is something else to consider. And then also, lastly, frequency and period. They did not clearly define what a period was. What does it mean that lateral has 15 hertz of frequency? I have no idea. So that is the things that I will be focusing on. And I can go on to my discussion. You don't have to.
Any comment?
Can we go to the problem statement? So it says that the balls start to collide and oscillate with increasing amplitude. And in your experiment, you only measured up to 60 degrees, but increasing amplitude means all the way until the very top where the amplitude cannot increase anymore. The path on the top is not equal to the path on the bottom. So how can you ensure that your model works for every position of the ball?
I'm not saying, the problem statement is not saying that we should do the experiment until it goes to here. It just said increasing amplitude. And I did track the increasing amplitude in the last
But
page.
only for certain positions. Like when you see someone playing lateral, it
Yeah,
goes all the way up here.
The last difference was the problem statement, because the problem statement didn't actually stimulate that we should, didn't actually certainly say that we should go all the way up to here. That's just some Indian.
So are you saying your model only works for angles below 60 degrees?
In my experiment, I only do until 60 degrees. But however, their amplitude will go upper than the 60 degrees.
And don't you think that not knowing the mass is an issue?
I'm not saying that I'm not knowing the math. I did mention
I
that
asked you,
I know
you
the
didn't
math.
answer.
I did answer. I'm sorry.
Both
Just
balls.
both. They're the same ball. One is
You measured both of them?
Yes.
What exactly is it?
yes.
Okay. And did you mention, in your report, did you take into account centripetal force?
Sorry.
Did you take into account centripetal force?
Middle.
Centripetal force.
I know the force that it was produced by the earthquake.
Because the problem statement says that if it oscillates around the vertical direction, and when you think about the pivot, when you think about oscillations, you would think that when the pivot goes up, the balls will be pulled towards the pivot. And I think that is a very important aspect to consider. Have you considered centripetal force?
I did.
Right.
You see, I just ensured that it's centripetal force.
Do you have data?
Oh, sorry,
Do you have data for centripetal force? Because I think oscillation
Because
and
I think that the most important in this from the statement is not the force. I think the most important is the resonance.
okay. Have you considered the possibility that the strings stretch and compress during the motion?
Yeah. So I have considered two types of materials of the spring. One is using the plastic, and another is using.
I'm not talking about the material. I'm saying that the string doesn't stay at a constant length throughout the motion.
So that's why I use the plastic string. So the tension of the string is very.
So you're assuming the string length stays constant.
In my experiment, that's what I observed.
Interesting. Do you think that
Can I
lateral?
add one? Because through this observation, you can see that the string is not always the same length, but this string is not. This string is not a plastic string, so that's why I choose plastic string instead of the.
Okay, let's move on. Do you think that lateral is a chaotic system?
Eventually, if you put too much force or the frequencies is not in the range, then it will be chaos.
Because I think it's pretty chaotic because
For all the time?
even if you try to replicate the initial conditions, it won't apply the same way each time. So how do you account for chaos? Because I think your model is too simple for how complicated lateral actually is.
Look at this chart. You can see that eventually there will become a constant amplitude. So that's why I don't think that it's always chaos.
Speaking of this graph, what does Hertz mean? How do you define one period?
Period.
Can you explain what the motion looks like for one period?
Usually, pandemic, the period of the pandemic is here, over here. And they have the same height, and this is the middle, right? And the lateral their period is half of it because they meet each other in the middle. So that's why we stop here.
Okay, so how many camera angles did you use during your experiment?
Cool.
Can you explain?
Pay attention to the setup here. One is here, and one is there, one is here, one is there, and one is here. To make sure that it's a 2D motion. In my simulation, I suppose that it is a 2D motion. So I track the two sides of the track.
Theta, do you account for the starting phase where the balls sort of stay together? Because I think that initial jump start that enables the balls to move further apart is also pretty important.
Can I ask you a question? Do you suppose that the lateral can just move while they're like this?
If you're oscillating it, like I'm asking like the initial phase when you're oscillating, how does it go apart when it's stuck together?
In my measurement, in my experiment, I'll do it like.
So you're not starting and hooked together. think you should come up with a model for how they initially separate. And that also an important process, like of the line.
Suggest what's the initial?
I mean, like, for the whole phase of ladder, it's not only the middle part, there's also the top part and the bottom part. I think you're only accounting for like a small aspect of the experiment.
I did lose count about the top part, but in the practice statement, I didn't actually see that it confirms that we have to calculate the output part, but I believe that that's my mistake. But that's not our main focus and not the main focus of the problem.
Since the problem statement asks about amplitude, can you like explain how frequency affects amplitude? Can you just like conclude your report more decisively?
In this chart, you can see by using the same length of the string but using different frequency, you can know that you can make. Can you see the numbers of them?
Yeah.
Yeah, you can see that their amplitude is different.
So how, like, let's say the frequency goes up, how would that affect the amplitude?
Oh. Through this chart, you can see that you agree that there's resonance.
Yeah.
So if there's a resonance, there will be a peak of the amplitude. So
But what's
this
the
is
relationship?
what's the relationship here? This will be
If hertz goes up, what happens to amplitude?
the amplitude will become bigger, but in only one
Okay, fine.
in only this range. It's not.
Oh, on the top it says force equals 2 times force of the system. Can you explain where the 2 times comes from?
I have mentioned that it is a half. It goes to the half when if you consider a simple pandemic period, then it will be goes to here. So it only goes to here. So that's why I consider that it's a half period.
So you're only considering the pendulum movement and not the collision? You're assuming it's like a pendulum movement, but we're not accounting for the rapid collisions.
That's
Because
they're common. They did. I did consider they did go together. So that's why that's the half period.
okay.
You don't agree that that's the half period?
No, that's not what I'm saying. I'm saying your model is pendulum, the simple pendulum model is too simple for this experiment. That's what I'm saying. Because there are a lot of other suggest you like a different method for the model.
Yes.
I think that
Okay,
maybe you should consider
Yeah.
other method.
opponent, please summarize.
Okay, so I'm going to summarize the discussion. So the first topic we talked about was amplitude. They do not account for the secondary contact at the top of the spin, and they clarified on some unclear equations. Frequency, they showed the correlation between frequency and amplitude, air analysis, potential string stretching, and they said they used plastic strings, which kind of doesn't make sense because the stretching happens throughout the experiment. Experimental camera angles, they said they have 4 initial conditions, initially pulled apart. They don't specify when they start measuring, and they don't start from rest, which is, I thought was pretty weird. Chaos, it can appear over time, and I think it is worth exploring for the reporter. And then oscillations, they clarified some confusing definitions, and they did not explore collisions.
Okay, so reviewer, please.
I'd like to ask the opponent that she had mentioned that she used a 2D model to describe this phenomenon. So do you agree with that?
No, I think it should be three-dimensional because they can contact at many different.
Okay, thank you. And to the report, I'd like to ask, what's the natural frequency of lotto?
Actually, that's not the current frequency. That's the frequency of the system. And the frequency of the system, I calculate
But you use
the result.
resonance. Natural frequency is an important part of resonance.
Yes, I know. So the system, natural frequencies is the material.
It's a material.
The natural frequency describes the materials.
So will natural frequency change while you play lotto?
What do you mention as?
Okay,
What do you mean that it's not natural frequency?
it's a natural frequency. People have a natural frequency. With you that, can you explain what's damping?
Damping is the loss of energy.
It's a loss of energy. Okay. And could you please turn to the formula, please? I think you should add some symbol to explain what is this, like F means, but because I don't know what it means. Okay. And you mentioned you have used the conservation of momentum, and you measure the velocity. So the velocity is the vertical way or horizontal way.
Because I consider it a horizontal, a vertical way.
Vertical. Okay, thank you. And can you turn to the result that amplitude to the one? Yeah. And you say that it will stay constant. So, but it will have a damping effect of that. So, how do you
Yes,
think?
but it will have the damping effect, but additionally you will add the force, right? When you're playing lotto, there's the force.
So,
The damping effect that I calculate is that when I believe that there's energy loss, although I give the force, but however, that's since the small, that's not
Where
very
did you use the
effective.
damping coefficient?
I used the damping coefficient when I didn't add another force of it.
Time's up. Yeah, reviewer.
I'm a reviewer from variable 1, and first I would like to review example number 3. And it's a problem statement. And it's an overview that she used the energy and the explanation function and resonance. And experiment she then the driving frequency. And this discussion part that she say energy decay in the beginning, so the system in elastic collision. And she didn't have any conclusion. And the strength for the reporter is that she has a complete theory and good time control, but suggestion against her is no equation for damping, and no explanation of each symbol, and no explanation of chaos. And the strength for opponent is he has a deep discussion with her, and the suggestion is he didn't understand the problem statement well. And discussion part that he asked her, did you do the experiment until 16 degrees? Yeah, and she say 50 degrees okay, but we think that they should do more experiment to make more aptitude to affect this phenomenon. And he asked that, does a string stretch? And she said he's composed, but she don't have any video to prove that, so I don't see any evidence. And he asked, have you considered the string is not constant, like become soft? And she said she used a plastic string, and we think that we can control the velocity that make the string remain tight. And we think that, and he asked, did you think it's chaotic? And she said, when it out of the certain range, it will be chaotic. And he asked, how many cameras do you use? She used 4 cameras to ensure it's 2D motion. But in a video from a report, we think that a lot of rotates, so it's a 3D motion. She can use the 2D motion to describe it. And how would frequency affect the amplitude? She say, if reasoning occurred, it is a peak amplitude. And we think that the driver frequency matches the natural frequency, and so the amplitude will increase. And I asked that, did the opponent agree to use 2D motion to describe it? And they disagree, and I agree with the opponent. In the video from the report, yeah, the same reason. And she measured the velocity she used the conservation of momentum. So she measured the velocity, and they say that she measured the velocity of horizontal wave. Yeah, I agree with that, because the vertical wave won't be the conservation of momentum. And I asked that, what is the damping? And he said it's an energy loss, but I think it's like a resistance that may affect this phenomenon, make it hard to move. And I asked, where did you use the damping? And they have calculated the damping coefficient, but they didn't use it. And
Time's up. Okay, reporter, please conclude.
For concluding remarks, there are some two that we want to say. And the first one is that they mentioned about the camera position. And we have 4 camera positions in different positions. And the opponent asks, is this a chaotic system? And the opponent says that they believe that the lateral is a whole chaotic system. But however, we think that only after a specific frequency or force. And they ask that vary the central force. And we don't think that the central force is the main factor for this problem. We think that the main factor is the frequency and how the oscillation frequency affects the amplitude. We say said that when there's resonance, the amplitude will constantly increase to a certain point. And they asked the tension of the string, and we answered that tension is a critical factor in this phenomenon, no matter what the string material is. And both of the reviewer and the opponent don't agree that this is a 2D model. However, we have placed the camera in forward position to confirm that it's a 2D model. And also, the reviewer says the natural frequency of the system, but the reviewer misunderstood the definition of natural frequency. What we mean is the resonance will occur when the frequencies of the motion hit the oscillation frequency. Thank you.
Okay. So questions from Julie?
Can you show me the equation of the behavior? Yes. Because from the problem statement, your pivot will oscillate along the vertical direction. So you're using your modified equation. Can you show me where is the external forces in your equation? It will generate the resonance behavior. You know it?
Control the same force for the experience.
So how can you prove the resonance in your equation? So the others, opponents, or do you agree? The equations, can you explain?
No, I don't agree, because she has added force on the lateral, so she had later add like a driver frequency or something like that.
Yeah, I think oscillation is a very important part of the problem statement, so they should have included it.
Because you say it's a frequency match, resonance occurs, right?
The resonance occurs when that's not exactly the half of the frequency of the force equals to the 2 times of the frequency of the system.
During your data, so you see the oscillate using time. So can you observe any resonance behavior in your observation?
Yes. And this, you can see that if there's resonance occur, then it will affect the highest amplitude of the system. That's 2.48, and the x is the 2.48.
Can you go to the last slide? This figures is directly on your observation.
Not up.
Or your prediction.
No, that's not my prediction.
So because you use the resonance to explain your result, do you think the pattern is a resonance pattern?
I don't assume that all these diagrams is resonance, but in my experiment, no matter does the resonance happens or not, eventually they will get the certain constant of the same.
So you think that when the resonance happens, the
Resonance happens
the
only
res-
affect the amplitudes.
and the amplitude will keep a constant in the end.
If I keep doing the same force and the same frequency.
Do you agree with that?
I don't agree. This pattern could show pretty much any pattern, it doesn't have to be amplitude. I think the main factor is not resonance, but rather centripetal force.
I move the forward.
More questions from you?
Okay. The reporter, you assume the angle is less than around 60 degrees.
No, that's only the initial, for the initial. But if,
Yeah. Okay. And what would be the difference in the angles, small compared to large angle? I think.
it will give a different, the potential energy will be different. Since
Okay.
this will.
So would that so the theory that you use will be different for small angle and a large angle?
I don't consider the Lotto as a
No, I'm
small
just
angle.
asking you.
Because no matter what initial angle it is, they will have a bigger angle, not small angle.
You want to add a little bit more? I mean, obviously the angle for the real Lotto could be much larger than 60 degree. So just briefly describe your viewpoint of your more complete theory.
I think it was an oversight on their part to not include larger angles because, for example, if it reaches the top, it might not follow a circular path downwards. So I think they have to account for like the change in path as well as different energy levels.
So what kind of model you should use then? What kind of model? Theoretical model, what kind of model? Just
Maybe a more complex version, like a double pendulum, perhaps.
I don't think the angle will larger than 60 degrees. And when the Lotto will have a amplitude maximum that make a tension that won't affect this the Lotto. And the maximum the main reason that will cause the maximum is the velocity and the amplitude.
Thank you.
Okay. Jury, prepare ready. Okay, first, for the reporter, 6, 5, 5, 5, 5. For the opponent, 6, 8, 6, 6, 6. For the reviewer, 6, 6, 6, 5, 6. Okay? So morning session is over.